Yes. Hello, everyone. My name is Carl, and I'm going to talk a little bit about unauthenticated encryption, what it is, and what problems it can lead to in practice. Super quick about myself. My name is Carl. I'm 26 years old. I'm a master's computer science from KTH here in Stockholm, and I currently work as the head of security at Kry. We are revolutionizing healthcare. And I'm a frequent CTF player for the mostly Swedish team Hacking for Soju. If you want to reach me afterwards, you can use any of these methods. So let's jump into it. Okay, cryptography is a very broad field, and you can use cryptography to accomplish a lot of different things, where smart people have developed, used math to develop algorithms to perform various tasks. The most common and the first you think of when you think cryptography is to encrypt, to hide data. But you can do other things as well, to sign it or verify that the data has been created by a certain person and so on. And these cryptographic properties are often accomplished by separate algorithms, which can be used and mixed and matched as individual modules. So unauthenticated encryption is what happens when you use the confidentiality property, that is, you hide the data without authenticating that the encrypted data has not been modified. So there are various ways to encrypt data. Typically, you divide into two broad categories, block ciphers and stream ciphers. And I'm going to talk about one specific block cipher in this case. So you have, or actually this applies to most block ciphers in general. But the most common one by far is AES, which is a block cipher. And that means it's used to decrypt one block of data. In the case of AES, you encrypt 16 bytes at a time. And that's the only thing AES can do. It can encrypt 16 bytes of data, no more, no less. So it's a very good algorithm. You use it together with the key to encrypt your data, and you can only decrypt it if you have the key. And there are no known practical attacks. But often you want to encrypt more than 16 bytes of data. So what do you do then? You use some kind of what's called a block cipher mode, where you chain together multiple uses of this algorithm to be able to encrypt larger pieces of data in a secure fashion. So one very common such mode is the CBC mode, the cipher block chaining mode. And this is a diagram of the encryption and decryption under CBC. So basically what you do is the ciphertext you get from encrypting one block is XORed into the plain text of the next block and then encrypted. And conversely, when you decrypt, after you have decrypted the block, you XOR it with the ciphertext of the previous block. So, and this is fine for encrypting and decrypting data, but there is no way for this algorithm to tell if this data that you feed it has been created by it with this key or so, because I mean it could potentially generate any data from the encryption algorithm. So basically it has to accept all input. And then there might be problems, or I mean ways to decide afterwards if this was actually a valid message or not. But that usually leads to trouble, as we'll see. And Moxie Marlinspike, famous security guy, he coined the cryptographic doom principle, which basically states that if you perform any kind of operation on encrypted data before verifying its integrity, it will lead to certain doom. So one such problem can be exploited with what's called a bit flipping attack. So if we think back to this, the CBC decryption scheme, at the end we just XOR the cipher text of the previous block into the plain text or the intermediate value, which becomes the plain text before receiving the final value. So that means that if we XOR something into the last block, the last byte of block X, we will perform basically the same. When this is decrypted, then it will perform the same XOR on the last byte of block X plus 1. It will also completely ruin the block we modified due to the nature of the encryption algorithm. But that might not be a problem for the attack. So an example of this is we found a vulnerability in an email service. So this email service, you connect it to your domain, and you can then send out emails, and your emails can contain links. And the links are not just directly links to where you're linking. They are actually pointing to a domain, to one of your subdomains, which actually points to the mail service. And the link itself contains the target URL encrypted. So basically, it has this form. You have some subdomain link, your company, and then there's some metadata, and then there's this big chunk of the encrypted URL. So, and this part is not authenticated at all. So that means we can perform this bit flipping attack on this encrypted data. So first of all, we need to know, to be able to calculate what we need to XOR with to create the data we want, we need to know what's in there to begin with. And that's easy. We just visit the link and see where it redirects us. So then we can just calculate what values we have to XOR into a block to modify the next block when it's decrypted. But as I said before, one block will be completely ruined. So for example, if the link is 3 blocks long, the first one will contain http://, and then the URL will follow. So if we take the middle block, modify it, so that we completely control the contents of the third block, and at the same time completely ruin the second block, we can just begin the third block with an @ sign, which will create a URL which will be http:// garbage @ and then a domain. So the garbage part will just be treated as a username, and you will be able to modify this link to point to whatever domain you want. And this might or might not be a problem depending on the other assumptions in this system. For example, if you have 2 loose OAuth settings, this might be used to steal tokens and so on. The other kind of attack that you can perform with unauthenticated encryption is what's called a padding oracle attack. So in the previous attack, we already knew the plain text and we could modify it to whatever we wanted. But we can actually also, in some settings, recover the plain text without knowing it by just asking the system to try to decrypt a value for us. So typically, what you do when you have data that is not, the length is not a multiple of 16 bytes, you pad out the last block. And you do this in a way called PKCS7, which just means that you put a number of bytes as padding, all containing the value of how many bytes you added. So if you have 12 bytes in your last block, you add 4 bytes, all containing the value 4. So that the algorithm, when it finishes decrypting, it will look at the last byte, it will see a 4, and it will remove the 4 last bytes, and then you have your final decryption. So, and in cryptography, something called an oracle. It's something that will basically give you some kind of answer, yes or no, to a question. And in this case, the padding oracle attack can happen when the system gives different error messages depending on if the problem was that the padding was broken or that the message it recovered afterwards was malformed. So if they receive, the algorithm receives a message and it decrypts and it sees that the last byte has value 7, but it can't find 7 sevens in a row at the end, then there's something wrong with the padding. If you have this thing where the system gives you different answers, it will enable you to, you can make a guess for the actual value of 1 byte in the ciphertext. So for example, we're trying to uncover the last byte of the last block. So we take a guess. It's somewhere between 0 and 256. And then, assuming this guess, we calculate what value we need to XOR in the second to last block to transform this value into a 1, which will make this a valid padding. You do this for all 256 possible values, and one of them will give you a different error message, hopefully. And that means that you have correctly guessed the value of that byte. And then you can just move on backwards. So since you know the last byte, you can just repair that part so it will say 2, and then you try to guess what's the second to last byte to make it a 2 as well. So you will have a valid padding of 2 bytes, and so on. So then you can move all the way down and uncover the whole block. And when you've done that, you can just remove that block altogether and move on to the next block, and so on. And you can then decrypt the whole message. And this is a lot faster than trying to guess the whole block in one. You just do 256. In the worst case, you'll do 256 tries per byte. And one particular example of where this was a problem was in a system I looked at once where in the admin interface, you could do backups of your configurations. And this is not necessarily like a sysadmin with full server access. It's just some person with admin rights in this particular system. So they could take a backup of the configuration, but the backup would be encrypted. So the system would take all the configuration files, it would zip them together in a zip file, it would generate a temporary key, encrypt the zip file with this temporary key, and then it would encrypt the temporary key with a master key stored on the server. It would give you those two things together, the zip file and the encrypted temporary key, and give you this encrypted file. So what we then could do was to just look at this first part, and this was encrypted with CBC. So we could use this padding oracle attack to uncover this temporary key, which then enabled us to decrypt the whole zip file. And then we could modify the contents of the zip file. And the thing is that what this system did when you uploaded zip file again to restore the configuration was that it just unzipped it in a temporary folder. The thing is that it didn't account for the fact that you can have relative paths in a zip file which goes upwards. So we could put in like files in this zip file with the paths like ... and so on, and then put files anywhere in the system where the application itself had write permissions. So this would then lead to overwriting some scripts and giving us remote code execution on the server. These are two attacks that arise from the problem of using encryption without authentication. So what's the solution? Well, use authentication. And what you typically do is you use something called a message authentication code. And one particular such that is popular and secure is an HMAC. It's a hash-based message authentication code. So you use it together with a key to create a tag from your message. It's kind of like a hash, but it's also dependent on the key. And then when you receive the message, you can take the key, the message, and the tag and verify that it's all consistent so that you know that the message has not been tampered with. Yeah, that's all for me. Thank you.